Greetings, everyone. Welcome to 4D chess. When people say someone is playing 4D chess, they usually mean someone is thinking several moves ahead of everyone else. But what if you could actually play 4D chess? Not just as a metaphor, but as a real playable game with proper rules, real piece movement, and genuine, open source, strategic depth. Today, I'm going to show you exactly that. Welcome to 4D Quadray chess. So if you want to play this, you can head over to the Doxology Quadcraft repo, head over to the 4D chess folder and just drag index.html into your browser, and you will have a fully geometry verified, tetrahedrally coordinated, isotropic vector matrix Quadray based chess game that you can select the pieces, move with the number keys, or you can move by clicking a spot, or you can make random moves and just watch the game play out semi-randomly. So, what exactly is 4D chess? Let's start with what it's not. It's not some impossible abstract concept you can't visualize, and it's not regular chess with a confusing coordinate system bolted on. 4D Quadray chess reimagines chess in a 4D tetrahedral space. If you want to learn more about quadrays, I recommend heading over to the Math for Wisdom, checking out some of the quadrays, checking out some of the Quadray information, looking at what Kirby Earner's doing on his blogs and YouTube, going to the Wikipedia for Quadray coordinates. Instead of the traditional flat grid you're used to, pieces move along four basis directions that emanate from the center of a tetrahedron, a pyramid made up of four faces. And here's those four directions of the quadray in the center, and every point in this space is going to have four values, A, B, C, and D. That's what's going to make it four-dimensional, is the fact that we can move along four axes. Think about regular chess for a moment. You have the x-axis to the left and right, and the y-axis forward and backwards. That gives you a two-dimensional grid. 3D chess adds up and down. That's the XYZ system. In 4D chess, Quadray chess, we do something different. Instead of four perpendicular axes at 90-degree angles, we use four axes that meet at about 109 degrees, the natural angle inside of a tetrahedron. The result is a game that looks like 3D chess when you see it on the screen, but the underlying coordinate system has four dimensions. Every position on the board is defined by four numbers, A, B, C, D. When you move a piece, you're sliding along one or more of these tetrahedral directions. So we can see that here. And we can play real chess, difficult as it may be to see because we're playing in a solid space enclosing game board. Let's talk about quadrays, the heart of this coordinate system. This is where it gets interesting. Quadray coordinates were developed as a synergetic alternative to the traditional Cartesian XYZ system we use every day. In Cartesian coordinates, you have three axes meeting at right angles. Simple, familiar, works great for rectilinear boxes and buildings. But nature doesn't think in right angles. Buckminster Fuller, the famous architect and systems theorist, and more, noticed this. He developed something called the isotropic vector matrix, or IVM, a space-filling arrangement of tetrahedra and octahedra that represent how atoms actually pack together. It's based upon 60-degree angular coordination instead of 90. Quadray coordinates are how we navigate this tetrahedral space. Imagine you're sitting at the center of a regular tetrahedron. Or you can put your arms up into the sides and feet in a lunge position, and the origin is your center of gravity. Draw a line from where you are to each of the four corners. Those four lines are your four axes, A, B, C, and D. Every point in space can be described by how far you travel along each of those four directions. Here's the elegant part. All four coordinates are non-negative. No negative numbers are needed. And also we could do all integer accounting as well. When you normalize quadray coordinates, at least one of the four values is always 0. This makes calculation clean and intuitive when you understand the system. The angle between any two of these axes is about 109.47 degrees. That's the tetrahedral angle, calculated as the arc cosine of -1/3. It's the same angle you see between the bonds of a methane molecule, CH4. So in a sense, we're playing chess on a carbon molecule. Let me walk you through what you're seeing. This is the 4D Quadray chessboard. Rendered as a 3D projection, you can rotate and explore, which I guess is itself rendered down to 2-dimension for your screen. White pieces start on one side, black on the other. When I click on a piece, you'll see it gets a yellow selection ring and green circles show all the valid moves. Watch the sidebar. It's updating in real time with the Quadray coordinates. The 4 numbers are color-coded. A is red, B is green, C is blue, and D is yellow. When I make a move, the system will show the coordinate transform, where the piece started and where it landed. It also calculates the distance traveled with a Quadray distance formula. This is the actual 4-dimensional math happening in real time. Here. The pieces you know and love all make the transition to 4D space, and their movement adapts to tetrahedral geometry. The king moves one step in any single basis direction. Just like regular chess, now there are 4 directions instead of 8. The rook slides along a single axis. Pick a direction and slide as far as you want until you hit something. The bishop moves diagonally, which in Quadray space means 2 axes change at the same time. So if A and B both increase, you're moving along a diagonal. The knight keeps its signature L shape, 2 steps in one axis, 1 step in another. With 4 axes to choose from, the knight has many more potential moves. So let's move a knight. Look at all those moves. Knight moves, as it were. The queen combines rook and bishop movement, sliding along axes or diagonals. The pawn moves forward along its primary axis and captures diagonally, just as you'd expect. Check and checkmate work as they do in regular chess. If your king is under attack and can't escape, you've lost. For those who love technical details, let me show you conversion formulas. When you take Quadray coordinates and convert them to Cartesian, x, y, z, here's how it works. X equals a minus b minus c plus d divided by the square root of 2. Y equals a minus b plus c minus d divided by root 2. And z equals a plus b minus c minus d divided by root 2. The distance formula is the square root of the sum of squared coordinate differences divided by 2. The basis vectors, the 4 canonical directions which have length root 2 in Cartesian space, that's 1 over the square root of 2, which keeps the math clean. Why build a 4D chess game, other than the mimetic enjoyment? There are deeper reasons. First, it's an educational tool. Quadray coordinates and the IVM are genuinely useful mathematical concepts. They appear in crystallography, molecular geometry, structural engineering, and more. Hashtag School of Tomorrow. Playing this game builds intuition for tetrahedral space. Second, it's a demonstration of visualization techniques. We're taking a 4-dimensional system and projecting it down so humans can interact with it. The same challenges arise in data science, physics, and computer graphics. And third, it's just a fascinating challenge. Chess has been extended to 3D many times, but tetrahedral 4D chess, that's new territory. The game includes autoplay if you want to watch games unfold. So up here, hit auto, and you'll watch the game randomly play out. I haven't added in any sort of intelligent play, but it's cool to just watch these pieces go at it. The math panel updates in real time as you hover and click. Console logging will show you the full details of every move, the Quadray coordinates, the Cartesian conversion, and the distance traveled. Here's the closing and the call to action. Oh, black wins by capturing the king. Long live the king! That's 4D Quadray chess, a real playable implementation of 4-dimensional chess using tetrahedral geometry and Quadray coordinates. It's open source, runs in any modern browser, and has a full test suite verifying the math. So check out the tests folder. If you want, try it for yourself. Check the link in the description. The project includes extensive documentation on the mathematics, game rules, and strategy. And remember, next time somebody says that they or someone else is playing 4D chess, ask them if they've tried the real thing. Thanks for watching. Key points. 4D chess is real and playable. Quadrays use 4 non-negative coordinates. Buckminster-Fuller characterized the isotropic vector matrix, close-packed spheres, geometry. 109.47 degrees, which is the arc cosine of negative 1/3. That's the tetrahedral angle of methane. All the familiar chess pieces have adapted movement. Real-time math shows you the coordinates as you update and play, and everything is open source at the Doxology Quadcraft repo, where there's other fun games like the regular Quadcraft browser-based tetrahedral Minecraft. So now, I hope that you enjoy. I hope that you come and play with us in the School of Tomorrow, learn, find out what's happening with Cascadian synergetics and all the other fun things that are happening. And thank you for watching this. Hope this has been interesting, and long live synergetics.